Okay, so let us continue with this problem of Lagrange multiplier method. So we have to find the extremum value, maximum or minimum, subjected to some surface Gx equal to C, and we are particularly looking at the problem in R2. So what happened? We have used implicit function theorem with the assumption that f and g has continuous partial derivative, and in a neighborhood we have assumed greater than 0. I want non-zero, but non-zero means in a neighborhood I can take less than 0 or greater than 0. So, it really does not matter. So, the problem by implicit function theorem reduces that to that I can write in that neighborhood y equal to g x in the neighborhood of x naught. Here I am using implicit function theorem very heavily, the full force of it, that I can write y equal to g x, and the problem is now becomes to function of one variable only, that you find the extremum of this function f x, which is f x g x subjected to x g x g g x g x g x equal to c. So, I have assumed there is some extremum. So, what will happen? A function of one variable, if it has an extremum, then it is surely a saddle point, right. So, I must have, so I should first look for, this is an extremum, so I should look for this equation f prime x equal to 0. Remember, I am still in a neighborhood, I want to locate this point. I know that, suppose I am assuming there is an extremum, I want to locate this point with this assumption that okay, g is fine enough, nice enough, f and g, f is also nice enough. So, I should look for f prime x equal to g, f prime x equal to 0, because it is a saddle point, extremum, at extremum f prime will be a continuous function with derivative, f prime x will be 0. But what is f prime x? F is little f x g x. So, if I apply chain rule, I will get it del f del x plus at x y. So, now I am trying to locate this point x naught y naught, plus del f del y g prime x equal to 0. This is chain rule. Let me put a tag here 1. I also have that I am on the surface x g of small g of x capital G x equal to c. So, g prime x is 0. So, if I take derivative, I will have right hand side is constant, so it is 0. So, let us put 2. Now, I have g prime x here, g prime x here. Let me just get rid of this g prime x, because g is an implicit function. I do not know what is g, because implicit function theorem just give existence, but I have two equations involving g prime. So, I can get rid of g prime. So, this will imply g prime equal to minus del g del x divided by, I am not writing x y again, del g del y, correct. So, put back in 1, that will give us what? Del f del x plus del f del y into minus del g del x divided by del g del y this is equal to 0. Now, del g del y, I have dividing, but I have assumed it greater than 0. So, this calculation is valid. So, what we will have from that, I can get rid of the denominator, which will give us del f del x del g del y, okay, maybe minus, plus del f del y del g del x equal to 0 at the point of extremum, correct? And I write it in a inner product form. Inner product this is precisely writing this line. So, x y is hidden here, I have not written, I am continued. So, what does it mean? What is this fellow? This is simply grad f, right, at x y. So, I have not used this x y, it is always there, but now I write this is grad f at x y dot with minus del g del y del g del x. What is that? Well, grad g is del g del x del g del y. What is minus del g del y del g del x? You see, if this is, I am looking at surface gxy equal to c. So, this is the gradient. So, this fellow, if you so this will give us 0. So, this is the gradient, this fellow is orthogonal to the gradient, right. So, this minus del g del y del g del x is orthogonal to the gradient, but here I have inner product, this fellow is 0. So, del f at x y is orthogonal to the gradient, which means it is parallel to grad g x y. Okay. So, let me write it here. So, grad f at x y, x naught y naught is parallel to because it is orthogonal to the vector which is orthogonal to grad g x y. So, that means this vector is some multiple of this. Two vectors parallel means they are multiple of each other, and instead of writing this way, I can take this side and I can adjust the sign. I can write this is equal to 0. So, what does it say? It says that if we go back to our original problem, that find extremum value of f x y subjected to gxy equal to c is equivalent to find extremum of correct. Grad h is 0. I should say not extremum, but I should say here extremum or not, that will depend. Saddle point, because equating to 0 gives you saddle point only. I will talk about it later, that this method only gives you saddle point. If it is the maximum or minimum or extremum or it is not, that depends on the geometry of the problem. So, we have reduced the problem of finding at least the saddle point of fxy subject to gxy to a function h, capital H, f plus lambda g, and you find the extremum. Now, how do you do it? Well, there are 3 variables here, x, y and lambda. Lambda you do not know, right? This is for some lambda. So, this is same as saying grad h x naught y naught is 0. So, I have to find locating this point x naught y naught, I have to put grad of that fellow is 0, which is del h del x 0, del h del y 0, del h del lambda 0. This is so called Lagrange's multiplier method. This lambda is called the multiplier. Okay? It's clear? Let me get back to the example and show how it is done, and how we have to decide its extremum or it's a minimum, maximum, everything. That depends on the geometry of the problem, and the example I wrote down that will illustrate this point very well. So, what was the example? Recall. So, find minimum distance from the point minus 5 0 to the parabola y square plus 4x equal to 0. As I said, as an illustration of implicit function theorem, that we can replace y square by minus 4x, x negative, but let us apply this Lagrange multiplier method here. So, this is what is fxy, what was fxy? Fxy was the distance from xy to this minus 5 0, that is 5 plus x square plus y square. So, find minimum, minimize this subjected to gxy is equal to x square y square plus 4x equal to 0. So, I will apply this Lagrange multiplier method. So, that by this method I should look at the function h x y equal to 5 plus x square y square plus lambda y square plus 4x. And then what I should do? I should look for the saddle point first. So, that is del h del x, how much is that? 2 into 5 plus x plus 4 lambda, that I will put to 0, del h del y 2y plus 2 lambda y equal to 0 and del h del lambda equal to y square plus 4x. We will get back the equation of G 0. From that 3 equation I have to solve x, y and lambda. Let us see. Now I have to be careful, as I said this will give us only saddle point because I have just put grad to be 0. Grad 0 does not ensure maximum or minimum. It may be maxima, it may be minima, it may be just a saddle point. Well, look at the equation 2. 2y plus 2 lambda y equal to 0. Okay. So, here was a picture again. So, as I said always while solving by Lagrange multiplier method always remember the geometry. This was a parabola and here is a point minus 5 0. Equation 2, if y equal to 0, then 3 will give x equal to 0. So, the point is the origin 0 0. And distance from minus 5 0 to 0 0 is simply 5, right. Well, again look at 2. If y not equal to 0, so I get this point which is a saddle point for h. If correct, if y not equal to 0, then 2 will give lambda I can cancel y here, that will give lambda equal to minus 1, which will give by 1 x equal to, well, minus 1 here, minus 4, how much? Minus 4 by 2, so minus 2, that is minus 3. Yeah, minus 3, 2, 2 into 2, 4, minus 4, 0. And y equal to from 3 or from 2 or 3, y equal to, no, from 3 only, y equal to so minus 3, 4 into 3, 12, so root 12, which is 4 into 3, 2 plus minus 3. So, one point here, one point here, and that is expected from the geometry because of symmetry. Any point here, there will be equal distance point in the below. Now, is it a minimum or maximum? So, the point x naught y naught now becomes minus 3 plus minus 2 root 3, and distance minus 5 0 to minus 3 plus minus 2 root 3, how much is that? From this is simply 12 plus so square root of f x y, this is 4. So, earlier from origin the distance was 5, here I get 4. So, this is a candidate. Now, is it minimum or maximum? Of course, it has to be minimum, right, because it is a saddle point and it cannot be maximum, because maximum distance I can go to infinity, because this is extended to infinity. So, maximum distance cannot be 4, because I can join a very point at a very far away to minus 5 and the distance will not be, it will be much I can make it be big as I want. So, it cannot be maximum, but why it is minimum? Well, I am looking for minimum of this fellow subjected to this thing, y square plus 4x equal to 0. That gives me so what you try to do here, I mean while solving the problem you do not have to do it, but actually you can show that you move little bit and calculate distance from minus 5 0 to this, and you show this is always greater than 4. That is very easy to show. Write down the formula, distance is greater than 4. So, distance is actually the answer 4. So, this is Lagrange multiplier method. I have illustrated it with for a function from of 2 variables. Now, what we will do if I have function of several more than 2 variables? Suppose I have the problem, instead of R2 I have R3. So, you have to find extremum subjected to a surface, level surface, the problem does not change a bit, it is same. What will happen? I will assume f and g has continuous partial derivative, and suppose x naught, y naught, z naught is a possible candidate. Then around the neighborhood, around a neighborhood theta, what will have? I will have that there is a function g such that y equal to g1x, and I will have function g2, okay, some other neighborhood, but I can take the minimum of that. So, this is implicit function theorem. And then problem reduces to finding extremum of h x y z, the same derivation, do it yourself. oh, subject to two condition actually, sorry, I need two condition here. So, if I have set one variable, I need one condition, and here I subject to intersection of those two surfaces, which is a curve. Okay, the same derivation will work. I mean, you go through the derivation, instead of del f, del x, del and del f, del y, here it will be involved del f, del x, del f, del x, del f, del y, del f, del z, and G1 prime, G2 prime. You will have three equations, you have to remove G1 and G2 from the equation, you will get back to this one. So, do the derivation yourself. I will put it as an assignment problem also. And now you see what will happen if I take u in Rn. And instead of 2, I have k many condition. Where k is less than n, to apply the implicit function theorem. So, I will have a neighborhood of x naught, the critical point, where I will have G1, G2, so on up to Gk. Same derivation will tell us that it reduces to finding extremum of Hx equal to and that is it, that is Lagrange multiplier method. And direct application of implicit function theorem. In the next set of last, that will be last two lectures, we will discuss another application, another very important application of implicit function theorem, which is inverse function theorem. Thank you.